Modern multi-agent systems rarely fail because the underlying models lack intelligence. They fail because the engineering teams building them drown in integration plumbing. When you deploy multiple specialized agents that must communicate with a fragmented ecosystem of external tools, Google Drive, internal proprietary platforms, GitHub repositories, you hit a scaling wall. Every new agent and tool added to the cluster compounds the integration overhead, as the number of possible connection points grows far faster than the systems can be manually updated. Engineering teams are forced to build custom API wrappers and translation layers for every single agent-to-tool interaction. This results in brittle codebases, where half the development cycle is spent managing protocol mismatches and maintaining bespoke adapters. Handing agents raw, unstandardized APIs directly causes two immediate issues. First, the verbose JSON schemas eat up the model's context window. Second, passing fragile API keys creates unnecessary security risks. To solve this at the architectural level, Anthropic introduced the Model Context Protocol, or MCP. MCP is a universal standard. It operates as a strict JSON-RPC 2.0-based client-server architecture, creating a single, predictable language for AI agents to communicate with external data sources. By decoupling the logic of how an agent orchestrates a workflow from the mechanics of how a tool actually executes, developers can scale agentic systems with far less manual intervention. To resolve integration bloat, MCP shifts the architecture away from a tangled web and towards a strict hub-and-spoke topology. At the center sits the MCP host. This is the overarching AI application, like Claude Desktop or a custom multi-agent orchestrator. Instead of agents querying APIs directly, the host manages integration by spawning dedicated MCP clients for each external service. Each client maintains a strict one-to-one connection with an isolated MCP server, a lightweight program housing the actual tools and data the agent needs. Because execution logic is isolated inside the server, platform teams can track telemetry, monitor API limits, and catch execution errors in one place, entirely separate from the agent's reasoning process. Before an agent can trigger a tool, the client and server must go through a mandatory initialization phase. The client sends a JSON-RPC initialize request. This is a formal handshake where the client and server negotiate exactly what capabilities they both support. The handshake verifies protocol version compatibility and forces the server to declare exactly which tools, resources, and templates it has available. This design makes MCP a stateful protocol. The client maintains an active record of the server's exact operational capacity before the host allows any tasks to begin. With the server's specific capabilities logged in advance, the host can validate the model's outputs against a known schema. This allows the system to catch and stop invalid tool requests at the protocol level before they trigger a failed external execution. During that initialization handshake, an MCP server can expose three specific primitives: tools, which are executable functions, resources, which provide context data, and prompts, acting as interaction templates. Designing these server tools introduces a strict engineering constraint. You cannot simply wrap an existing developer API. The tools must be designed with an LLM-First interface. A recent implementation by DeepSense.ai for an enterprise document processing architecture illustrates exactly why this matters. Exposing raw, developer-centric APIs directly to an agent causes immediate reasoning failures. Standard APIs rely on deeply nested structures that models struggle to parse and choose between. Furthermore, a raw API forces the agent to make sequential calls. To process a document, the LLM must manage authentication, upload, configure parsing, and request extraction as separate steps. The solution is wrapping these operations into a single composite tool within the MCP server, like parse document. The server handles the multi-step execution internally. The agent is presented with a strictly typed interface requiring only the document ID and specific parsing options. This structure prevents the model from generating ambiguous parameters. Abstracting complex API logic into single composite tools clears the token budget rapidly. In the DeepSense.ai deployment, this reduced context window usage by over 50%. However, abstraction can go too far. If a tool is too generic, the model lacks the necessary granularity to reason about what the tool actually accomplishes. Optimal MCP efficiency demands that tool schemas be designed around the limits of the model's reasoning capabilities and its token budget, rather than prioritizing developer convenience. Inside a complex multi-agent pipeline, you will have distinct roles. One agent handles task definition, another processes data, and a third extracts insights. This chart maps those agents to the available MCP tools. Notice that not every agent has access to every tool. Each is restricted to a subset required for its specific role. If you overspecify tools and grant every agent access to the entire server directory, you create interface bloat. This induces cognitive overload for the LLM. Presenting unnecessary tools to specialized agents burns through the token budget and significantly increases the probability of hallucinations during data manipulation operations. Beyond efficiency, there is a security imperative. Agents operating across multiple domains, interacting with external data, are prime targets for prompt injection attacks. A recent vulnerability in the GitHub MCP integration demonstrated how this vector works. An attacker placed malicious instructions inside a public repository issue. When an agent accessed that public issue, the prompt injection hijacked its instructions, commanding it to extract sensitive data from private repositories. The attack succeeded because the agent had broad, unscoped permissions across the entire GitHub ecosystem. Isolating tool access to the bare minimum requirements neutralizes this lateral movement. Applying the principle of least privilege to MCP tool exposure is mandatory for maintaining system stability and data security. All of these execution rules exist within the data layer. To move that data physically, we have to look at the outer layer of MCP, the transport layer. Developing an MCP server locally looks very different from deploying it to production. Local development typically relies on the Stdio transport, communicating directly between local processes on the same machine. While it provides zero network latency, it is strictly limited to a single client subprocess and cannot scale. For remote, network-accessible servers, production deployments must upgrade to the Streamable HTTP transport protocol. This relies on HTTP post requests from the client and server-sent events streaming back from the server. Moving to a network architecture requires containerizing the MCP server, typically using Docker, rather than running bare Python scripts on a virtual machine. Containerization provides the necessary sandbox isolation. It restricts the execution environment, preventing a compromised MCP server from accessing the host file system. Because Streamable HTTP exposes a single /MCP endpoint to the network, you must place a reverse proxy, like Nginx, in front of the container. This proxy layer serves as the primary defense boundary. It handles TLS termination for secure transit, restricts access via CORS, and validates bearer tokens before the request ever reaches the server logic. Finally, running this at scale requires deep observability. Integrating tools like Logfire allows engineering teams to trace the flows of the agents, catch tool execution failures, and monitor exact token costs in real time. Transitioning an MCP prototype to enterprise production requires taking this new AI protocol and wrapping it securely in robust web infrastructure. When assembled, the entire production system forms a clean, observable matrix. Multiple specialized agents operate through a centralized hub, securely querying a library of containerized MCP servers over Streamable HTTP. This architecture standardizes the integration layer, moving away from the cycle of writing and maintaining custom API adapters for every individual agent. The context window economics are optimized because the servers expose LLM-First composite tools, giving the models exactly what they need to reason effectively without token bloat. Attack surfaces are minimized by combining strict role scoping with Dockerized, network-isolated server deployments. As AI systems evolve from isolated language models into autonomous workflows, standardized protocols like MCP are the required infrastructure layer to ensure multi-agent ecosystems can scale without collapsing under their own integration complexity.